Yeah, typical class. Okay. So last time we were talking about electric forces. Where say we have two charged particles, Q1 and Q2. They're separated by a distance r, and we know the force between these two particles. It's given by Coulomb's law. Okay. Now, this raises an issue that has kind of plagued scientists for quite some time before this, going back to the days of Isaac Newton. So when Newton came up with his theory of gravity, let's just say look at the Sun-Earth system. So we have the Sun, and we have Earth orbiting around the Sun. And Newton explained that, and he said things tend to go in straight lines, just inertia, unless they're acted on by an unbalancing force. And so the unbalancing force in this case is gravity. The Sun is exerting a force on the Earth. And this was actually kind of seems trivial maybe, but no, this was actually, his work on gravity was one of the most important scientific accomplishments of all time. It kind of, by itself, it was extremely important. But it also kind of really, the scientific revolutions that started with Galileo and Descartes and those, really picked up with Isaac Newton's work. It goes beyond just gravity into just mechanics in general, how objects interact with each other. But again, he was actually criticized by some for his theory of gravity because they asked the question, how can the Sun exert a force on the Earth if there's nothing between them except for space? And Newton had a brilliant solution to that problem, which was to ignore it. And that's basically what he did. He was aware of the problem, he just didn't care. I imagine he thought about it, tried to come up with some explanation, but didn't. But his theory worked, and it was extremely important. And so he published it anyways, and kind of just dismissed his critics. Didn't care. And again, I do mean that that was a brilliant way to approach this problem, because if he kind of decided that's a flaw in his theory, that he can't explain this one part of it, then, I'm not going to bother publishing it. Well, we would have missed out on one of the greatest scientific discoveries of all time. So it was, good that he just dismissed the critics and published his imperfect theory. And, it kind of remained that way for several hundred years, where there was this issue of action at a distance. That's what they call it. How can this object exert a force on this object if there's nothing between them to transmit that force? I think a force is like I can push on this. Well, it's easy to see how that's exerting a force. So, again, this problem existed for quite some time. That changed in the 19th century, during like the 1800s, when this idea of a field came about. So, like, this topic is on electric fields. There's also gravitational fields that apply between the Earth and the Sun. And so, what we're going to do, I'm going to write down a couple names for stuff. There's Faraday and Maxwell. These were two of the most important scientists of the 19th century. Kind of an interesting pair. They worked independently, but their work complemented each other. And Faraday in particular is very unusual because he didn't have too much of an education. He got a job at a laboratory as an assistant, and without, really any scientific training, and in particular, he didn't know much about math. And he turned out to be one of the greatest physicists of all time, despite never really learning formal math. From what I've read, it's hard to believe, but he would really struggle in a class like this just because of algebra, just manipulating equations. So that's a very unusual trait for a physicist to have. Now, I've also heard people say that Faraday can actually be considered a very great mathematician, even though he had no training and didn't really manipulate equations. He didn't work that way. But they say he had a really amazing mathematical intuition that was just never, formalized in the form of equations, but he could just see things. Definitely a great scientist, either way. And he focused on doing experiments, and he did a lot of really amazing experiments focusing on electricity and magnetism. And it was Maxwell, we'll talk more about Faraday, like one of his most important discoveries, something called Faraday's law. And Maxwell is the one that kind of completed the subject. So it's like Faraday collected all this data and did all these experiments and made all these discoveries, and Maxwell was a great physicist, a great theoretical physicist, as well as a mathematician. He was like a master of just mathematics, and he was able to put all these experimental results in this very solid mathematical foundation. And he kind of completed the subject of electromagnetism, or at least like the classic subject of electromagnetism. Together they came up with this idea of field. So I'm going to start out by just doing a little algebra here. Hopefully Faraday doesn't object to this. Okay, so here we have Coulomb's law that describes the interaction between these two charged objects. And in a sense, this is just a very straightforward thing. You want to know the magnitude of the force between them? Just plug them into the equation. What could be simpler than that? What we're going to do seemingly complicates it, but not too much. We're going to take this one-step process, just plug things into equation, turn it into a two-step process. But I'm going to ask a question in particular. Say we want to know the force on charge 2. So we call that F2. That's what we want to know. So we take Coulomb's law, and I'm just going to rewrite this in this form. So again, exactly the same thing as we had before. But what we're doing is we're separating it into pieces. This first term here, we have Q2. This is a property of charge 2. Where this other piece only depends on charge 1. And like the distance between them. And so what we're going to do is we're going to define something called the electric field. I'm going to write this over here. I'll write our constant again. Okay, so that's our constant. So we define the electric field due to a point particle by this equation. Now again, that's just the magnitude of the electric field. The electric field also has a direction. We'll talk about that later. And so we can say the force on object 2 would be the charge of object 2 times the electric field due to charge 1. So the way we think of it, one advantage to introducing this idea of a field is, if we want to talk about forces, we have to have two charges that are interacting with each other. But now by introducing this idea of a field, we can talk about the electric field of just an isolated object, like charge 1. So let's say that charge 1 is the only thing that exists right now. Say in this region, there's only one charge, Q1. I draw it as a positive charge. So we have a charge here, and this new way of looking at the problem is we see that there is a field surrounding this charge. So just because this charge is here, this charge has an electric field associated with it that exists throughout space. Now the electric field gets weaker, like R is the distance. So let's say we have a point here. Say there's nothing at this location in space, but we have a point here, and there's a distance r between the charge and this point. And we can talk about the electric field at that point due to this charge. So this electric field just exists around this charge. And this gets us away from this idea of action at a distance. Because now if we place, let's say we have charge Q2, which was so far away that it wasn't really interacting with charge 1, let's say we move Q2 over to this location. Now, we can say, well, Q1 isn't doing anything to Q2. Q1 is not exerting a force directly on Q2, but there was an electric field at this location, and charge 2 is interacting with that field. And so that's how we get away from this idea of action at a distance. That, how does this charge exert a force on this charge over here? Well, there's an electric field here that's actually interacting with charge 2. And so, now if we want to know how charges interact, we, instead of just calculating the force directly, what we do is we find the electric field at this location due to this charge, and then we find the force on the charge. So we've got 2 steps instead of 1. But again, it doesn't really add anything to the complication of it. It's more of just a different way of looking at it, and a much better way of looking at it. This idea of the field, not so much because of action at a distance being a problem, but it's really nice to be able to talk about an electric field just being associated with a charge, not having to deal with multiple charges interacting with each other. That's going to prove to be very advantageous. And this idea of an electric field, this takes on its own kind of reality, where, let me just give you an example, which we're going to come to much later in the class. There's something called an electromagnetic wave, where I can draw it. We have an electric field. If we were to take a picture, it would look like this. So I'd say this is the electric field, just at one moment in time. So the electric field is different at different places. Now, ultimately, this electric field was created by a charged particle, but this is a very real thing I'm describing of. You might have heard it before. It's called light. Now, I just drew the electric field. There's also a magnetic field associated with it. We'll talk a lot more about that later. But again, just the electric field having its own existence, we do treat these things as being very real. They exert forces on things. They can store energy. An electric field is a very real thing. Okay, so, and it's just nice that we can get away from, when we're talking about the electric force, we don't have to look at pairs at least, or interaction of multiple particles. We can just focus on single particles. I think that's probably a very big advantage to that. Okay, so electric fields are real. So let's describe this 2-step process. So again, we have 2 objects, say Q1 and Q2, separated by a distance r. And so now if we want to know the force of interaction between them, say we want to know the force on 2, the 2 steps are find the electric field at the location of that charge. That's step 1, which we've pretty much done except for the direction part. We'll talk about that as well. So again, the electric field, we can easily calculate the magnitude. We still have to talk about the direction. Step 2, the force on the charge. Now I'm going to write this over here. The force on a charge is just the charge times the electric field. Okay, but I kind of put off direction. We really need to focus on that now. So let's say we have a positive charge. I need to draw a line down the middle. So we have an isolated positive charge. I'm also going to draw a negative charge over here. But again, let's say these are extremely far apart. That's why I put this line down the middle. They're not interacting with each other. We'll say they're just both extremely far away from each other. Okay. And so how do we represent the electric field? It has a magnitude. It also has a direction. It's a vector field. So like every point in space around this positive charge has a vector. And that makes it a little difficult to draw because a vector, we represent those with arrows, which, we have to draw an arrow at every point in space. How do you even do that? Well, we just don't draw them at every point. So we could pick, let's say we have a point here, just some random point P. And so you draw a line connecting our charge and our point. And so again, the distance between the charge and the point, that's R. We can calculate the magnitude of the electric field. As far as the direction, the rule is if you have a positive charge, the electric field points away from the charge. Similarly, let's look at over here. We have a negative charge. And electric fields point towards negative charges. So again, this is just, say, an empty point in space. There's nothing there. We don't have to have another charge there. We can just say there's an electric field surrounding our charge. And so it has a direction. Remember, they move away from positive charges, and electric fields point towards negative charges. Okay. And so basically, I guess in a sense, we're done talking about electric fields. Well, we're not really, but what we need to know is the magnitude and direction. So here's the magnitude, here's the direction. Depends on whether a charge is positive or negative. And again, we can just draw this vector at any point in space. This doesn't really give us too much information. If we look at, say, another point in space, we'd have another vector. I'm going to look at a point farther away. We'd have a smaller arrow because the electric field gets weaker. If we look at a point right next to it, we'd have a much bigger electric field. And so you can learn a lot about, just by picking points and just, they always go away from the charge. So if I draw a point here, there's a line connecting them, we go in that direction. So if it's a positive charge, the electric field always points away, and the magnitude depends on how far away it is. So that's one way we could kind of visualize the electric field, just by picking points and drawing the electric field at various points. We can't do it for every point, but if you draw enough points, you can kind of see what it looks like. There's another way that we can represent electric fields, and that's what we call electric field lines, which is usually what we do. So I'm going to just draw a positive charge. And I'll just draw what the electric field lines would look like. Basically, you can imagine drawing a lot of points and then just, connecting them. You draw enough points, you can see what direction they're going. So here, if we have an isolated positive charge, the electric field lines would look something like this. Now again, how many do you draw? Well, you can keep drawing as much as you want. We can draw more lines. Point is, they're moving radially outwards. So these field lines, they start on these positive charges and move outwards. Okay. Now, if we had a negative charge, it would look exactly like this, except the arrows would be reversed. They'd be moving towards the negative charge. Now, what if we had, again, we can calculate the electric field of a point charge, but what if we had 2 point charges? So let's look at that situation. Say you have Q1, I'll draw a positive charge here and a negative charge here. Let's say they're both kind of the same magnitude. This object actually has a name. This is called an electric dipole. 2 charges kind of separated by a distance d. That's called an electric dipole. And these are actually extremely important. Couple reasons why. But, one is that these kind of exist, usually not in this simple form. We have like a positive charge here and a negative charge here. But in like a molecule, like say you have a neutral molecule, you have your positive and, it's made up of several several atoms, each with its, positively charged nucleus and the electrons around it. However, the charges are not always symmetrical. So you can have a molecule with like some complicated shape, and maybe one end is going to be more positive and the other end is going to be more negative. And we can approximate this as, this situation. We have very simple, just one charge here, one charge there. So again, this is more complicated, but we can approximate that as a dipole. So, a lot of molecules have what's called a dipole moment because their charges are not symmetrical. So even though it's neutral, this positive charge over here is equal to the negative charge here, they're separated. And so we have this situation. Now, even if we had a symmetrical atom, for instance, we can turn it into a dipole. So like say we have a nucleus, which is your positively charged nucleus, and say we have a nice symmetric molecule. So the electrons surround it in like this cloud that's nice and spherical. And we can actually turn this into a dipole by introducing an electric field. Like say we have an electric field, what that's going to do, we're going to talk about this part of the equation next, but this electric field is going to cause the positive charge to go to the right and the electrons to move to the left. And so it was symmetric before, but now the charges are redistributed. Like the positive charge is over here, you've got more negative charge over here, and this is called an induced dipole because it was induced by this electric field. So again, dipoles are important. Let's get back to this. So we have two charges, and let's pick some random point, P. And we want to know what the electric field is at this point, P. I'm going to erase this for now, so we don't need that. And the rule is basically just what we did before with electric forces. It obeys linear superposition. So let's draw lines connecting each charge to this point. Now this is a positive charge. So the electric field points away, let's call this Q1 and Q2. To say that they're equal in magnitude. Okay, so the Q1 is positive, so E1 is going to point in this direction. Points away from Q1. Now what about Q2? Q2 is negative, so the electric field is going to point in this direction. And you'll note that I made this electric field, drew the arrow as being longer. And the reason why is if these are equal charges, E2 is going to be bigger than E1 at this point because this point is closer to charge 2. So the closer you get to the charge, the stronger the electric field. And so the net result, remember we have this parallelogram rule for adding vectors, the net electric field at point P is going to be, say, in that direction. So in principle, if you have multiple charges, you can use linear superposition. We know how to get the electric field due to a single charge. But what if we have multiple charges? Again, just calculate the electric field due to each charge individually at that point, and then add them as vectors. And so, in principle, pretty straightforward thing to do. If you know where all your charges are, you can calculate the electric field at any point. You can imagine in practice this would be kind of tedious. We have a lot going on here. We have to find the magnitude of E1 and E2 using this formula, where we'd have to know where Q1, Q2, and this point are, like in some coordinate system. So we have to know where all these objects are, or where these objects are and that point is. And then we can find the magnitude of E1 and E2. We need to know what direction these electric fields are pointing. That's based on geometry. And then to add them, we'd have to break them up into components and add the components. This process is basically identical to what we did with forces. yeah, the only difference is we're calculating the forces directly, where we had, like, instead of kq over r squared, we had k q1, q2 over r squared. So there's really nothing new with electric fields. It's the exact same procedure we did for electric forces, except we just have one charge instead of two when we're calculating these magnitudes. So I'm not sure. Maybe I'll do an example. I guess it doesn't hurt to have more examples, but for now, let's just kind of move on. So we get the idea. If we have any number of charges, in principle, we can calculate the electric field at any point using the formula, the directions from geometry, and this idea of linear superposition. But I'm going to go back to these electric field lines. I'm going to expand this dipole a little bit. So we have, say, a positive charge here and a negative charge here. Say we want to know what the electric field looks like. I'm going to draw the electric field. If you look at any point on this line connecting them, let me just pick one point here. So again, we have two charges, Q1 and Q2. So again, we'd have to calculate the electric field of each individual. So if we look at this point, E1 is going to point to the right. Because we're at this point, we move away from positive charges. I'm going to actually draw that over here, just as just kind of leave this board up here. And a negative charge would look like that. And again, I drew a line between them. Otherwise, we have this situation. In this case, these charges are close enough that we're going to be looking at a field, where they're interacting. The electric field is going to be determined by both. So you have to look at these as isolated charges. That's what the electric field would look like. So yeah, we're at the point here where, again, if you look at, like, say, this point here, where the arrows are pointing away from the positive charge. Now, E2, that's the electric field due to charge 2. So again, at this point, we can see electric field lines point towards negative charges. And so E2 is also going to be to the right. And so if we add these two, it's just going to point to the right. And so we can tell that on this line between them, we've just got a straight line from positive to negative. Okay, that's one line. Obviously, we'll do a little more than that. I'm going to look at a point here, kind of right next to this positive charge. And so, in this case, R in this formula is going to be very small. So we're dividing by a very small number. What happens when you divide by something that's small? You get something that's big. And so E1 is going to look like this. Where E2 is going to be, R for charge 2, it's a much greater distance. So E2 is going to point in this direction, towards the negative charge, but it's going to be a lot smaller. Sorry, that was E2. This is E1. And so again, this parallelogram rule, it's going to be, like, normally if Q1 was the only charge that existed, if you look at this point, the electric field would just be radially away. Now, the presence of this negative charge kind of tilts it a little bit towards the negative charge. Like, say Q1 was by itself, the electric field points in this direction. Then you bring in Q2, it kind of just curves it a little bit in the direction of Q2. Okay. Now, similarly, if you go near Q2, it's a little harder to draw it at this point because it's pointing towards charge 2. But again, it's going to be going basically towards this negative charge. So again, if you're near Q2, the electric field would point directly towards it. If it was an isolated charge, the effect of this positive charge would be kind of pointed away a little bit. Just, change that angle a tiny bit. But the closer you get to this negative charge, the less influence the other one has. And so, yeah, I don't want to clutter up the picture with all these vectors at individual points. So again, now let's look at a point kind of right in the middle. So like say we draw a line through this midpoint. And we look at some point, so it's equidistant from the two. And again, remember these are equal charges in magnitude. So if you look at E1, that's, you're at this point, you move away from positive charges. Picture you're standing here, like imagine you don't like negative charges, or sorry, say you don't like positive charges, but you do like negative charges. So if you're here, you want to get away from this positive charge as quickly as possible, you move directly away from it. You like negative charges, so again, E2 is going to point, you're going straight towards charge 2. But what we can also say about this is that these two vectors have the exact same length, because the charges are equal in magnitude and the distance, that r, is also equal. So these two vectors have the same length, they're just pointing in different directions. And again, if we draw this line here, these angles have to be equal as well, just due to symmetry. Because it's the, like these angles would have to be the same. Because this point is, these distances are the same. And obviously they share this line. So just from these triangles, like the tangent of this angle would be that distance over the shared side, tangent of that angle. These two are equal distances, so these are equal angles, which will make these equal angles as well. I think I probably made that more complicated than I need to. So the result is, if we add these two up, like the vertical components cancel out. So if you look at any point on this midpoint line, I'm going to try and redraw that a bit. But easier just to start over, actually. So we have our positive and negative. So we had that line before. So again, if I draw this midpoint line, at any point on the line, the electric field would have to be in this direction. And then if you look at like near this positive charge, we can, if we're close to the charge, we can consider it kind of like just an isolated charge. Because when we're close to it, the electric field grows very significantly. As R decreases, the electric field blows up. And so, the other ones can have such a tiny influence if you're very close to it. So we're kind of picturing together what this might look like. Let's say we look at going from this positive charge, we completely ignore this negative charge when we're close to the positive charge, because this one dominates. But then if we just kept going in this, if it was an isolated charge, we'd keep going in this direction. But now that we're getting farther from this charge and closer to the other one, this one doesn't dominate quite as much and it starts bending. And then this negative charge starts dominating more than the positive one. And so it's going to curve like this. And you can kind of see how we could build up what the electric field would look like overall. Actually, I'm going to try and post a picture. You can actually see the electric field. I'm remembering from a book, I'll have to dig this up, where you can actually take a picture very indirectly of an electric field where they have some substance that can kind of visibly line up with the electric field. So kind of like magnets, if you put iron shavings, you might have seen those pictures where the shavings kind of line up with the magnetic field. There's an example of that with electric fields as well. So I'll try to remember to actually post a picture as well. But I'm going to draw what the electric field for this dipole would look like. can draw several of these lines. Now this one is going to loop way around, kind of off the screen kind of thing. So it's moving outwards. Similarly with this one. So it's going to make this huge loop. Come around back here. And we can get some kind of an idea of what the electric field due to this electric dipole looks like. Okay. Now, one thing, kind of a random thing, but you might have been wondering, why do we call this a dipole? And ultimately, I think it comes down to looking at like magnets. So when we talk about electric charges, we call them positive and negative. Now later we're going to talk about magnets where they kind of have like magnetic charges, but historically they are called poles because, you know, the first use of a magnet is they point north. So you can have a magnet, it points north. And so it points towards the North Pole, so they started naming them poles when it came to magnets. And so it's something called a magnetic dipole. Like if you just have a bar magnet, that's a magnetic dipole. So I think that term just carried over. That's what we call this, an electric dipole. Okay, so there's some properties about electric field lines that are important. One is, we can kind of see from this picture that electric field lines start on positive charges and end on negative charges. And they have to do that. So an electric field can only start on a positive charge, and it can only end on a negative charge. So here it's like this one creates an electric field line, starts here, loops around, it finds this negative charge, and it ends. You can never have a situation like this, where say you have a positive charge, and the electric field line just does this and then stops at some random point. So you can never have an electric field where the electric field line is just going in this direction, and then it just suddenly stopped. The only way it can stop is if there's a charge there, a negative charge to stop it. Similarly, you can never have a situation like this, where an electric field just starts at some random point in space where there's no positive charge here. So they have to start on positive and end on negative. Now another thing about electric fields, I'm going to erase this dipole. Another important thing about electric fields is they can never cross each other. So let's say they can have more complicated shapes than what we're looking at. Let's say we have an electric field line that looks like this, and another electric field line that looks like this. Well, this can never happen. Reason why, this electric field line gives you the direction of the electric field at any point. So let's say we look at this point, what direction is the electric field at this point? It's in that direction. And it's in this tangent direction. I like to visualize it like, say you're drawing this line. And if you follow this curve, you keep just following it. But imagine just going along this line, but once you reach this point, then just go straight. Forget about what the line's doing. So kind of just go whatever direction you were going before you hit that point, then just keep going. And so if you look at this point here, the electric field has to be pointing in this direction because it's on this line. It also has to be pointing in that direction because it's on that line. And again, an electric field can only point, like at any point, the electric field has to point in a particular direction. And so electric field lines can never cross each other as well. So they can never start unless they can only start on positive charges, they can only end on negative charges, and they can never cross each other. So some basics about electric field lines and just electric fields overall. I think I might, I'll do this on a separate video, I think. Maybe I'll do one example of just finding an electric field due to some combination of charges. And again, the reason I was kind of hesitating to do this is because it's going to be basically identical to what we did with electric forces. However, the reason I'm going to actually do it is because, more practice you do, the better. So it doesn't hurt to do an extra one. So I'll do that in a separate video, though. So that'll be it for this one.